Good morning. We'll let everyone log in, so we'll get started in the next 30 seconds or so. Good morning, everyone. My name is Amanda Link. I'm the communications specialist here at the New York State LTAP Center Cornell Local Roads Program. David is in Ohio at our national meeting. Today we have Willy Grimmke presenting on bridge basics. I will let Willy explain his background and all of his knowledge. If you have any questions, you can throw it in the Q&A and I will be in the background checking. There will be PDH questions if you have to be on 90% of the webinar, and we will send you a PDH certificate after the webinar is over. If you have any questions, just email me at ael234@cornell.edu, and I'll turn it over to Willy.
Good morning, everyone. I'm Willy Grimmke. I'm an instructor for Cornell Local Roads. My day job is working for Greenman-Peterson. Long ago and far away, I was the county highway superintendent in Washington County, New York, where we owned about 110 bridges. Now, my background prior to that was in transportation and transportation-related stuff, highways and traffic and airports and the like. And bridges weren't really something I had spent a lot of time with, but when I started with the county, I got a crash course in being an owner and steward of bridges and a wide variety of them. So part of this is geared toward giving potential bridge owners the quick course in knowing some of the things that I wish I had known when I took over at the county and got to be the steward of bridges. So we will move on here. So our learning outcomes this morning. We're going to describe what constitutes a bridge. What is one? Then after that, you should be able to list the components of a bridge, discuss how a bridge carries loads, and describe common materials used in bridges. And then finally, you should be able to list things to look for as a bridge owner. So before we get too far along, I want to do a little poll question. You know, what's your primary, we'll start out with what's your primary job function, public works staff, I think I advanced one too many. Nope. Okay. Who do I work for? Town, county, city or village, state or federal, tribal, private, or the weekend? So if you will answer the question.
I don't know what's going on with the poll, but
Okay.
let's try the next one.
Okay.
So I have, what is your primary job function?
Yep.
Okay, so let me launch that. All right, here we go.
All right. Primary job function, admin, superintendent commissioner, engineer, field crew, board member, or I don't do any of that stuff. Okay. Got 3% admin. We've got some supervision folks. We've got a bunch of engineers, some field crews, board members, and none of the above. All right. And next, who do you work for? Village, town, county, city, state, private sector. Okay, survey says got a good representation from counties, got some from towns, some from city and villages, some state folks, and federal. Okay. Okay, let's move on here. How long have you worked with bridges? Less than a year, 1 to 5, 5 to 10, 10 to 20, or over 20 years.
Poll is fighting me today, but could you guys put that in the Q&A?
Okay, we got less than a year.
Ten to 20, over 20, 5
20.
to 10.
So we've got quite the range. We've got folks that can probably teach this with 20 years of fooling with bridges, and some who are totally new to it. So for those of you that are experienced, I'll try not to bore you. And for those that are new, I'll try not to go too fast and make your head swim. And how many bridges are in your system if you are a public agency and steward of bridges? None, 1 to 10, 10 to 25, 25 to 100, or over 100. And we'll go back to the Q&A. Okay, we got somebody with a boatload. We've got a few with quite a few. And the not sures. All right. Okay, so we will, now that we kind of have an idea of who's got what, we will move on. So what's a bridge? This is a photo of the Ogdensburg Bridge and Port Authority bridge over the St. Lawrence River between the US and Canada. This is without a doubt a bridge. It crosses the river. We have the suspension bridge span in the middle. We have deck truss approach spans on either side, and then out of the field of vision, we have plate girder approach spans. So this, without a doubt, is a bridge. But by definition, what is a bridge? Well, the feds in the CFR 23 CFR 650, they define a bridge as a structure including supports erected over a depression, obstruction, such as water, highway, railway, having a track or passageway for carrying traffic or other moving loads, opening measured along the center of the roadway of more than 20 feet. That's the magic number. Between the undercopings of abutments or spring lines of arches or extreme ends of openings for multiple boxes. It includes multiple pipes where the clear distance between openings is less than half of the smaller contiguous opening. So yeah. What does that really mean? We'll get to that with some photos in a minute. Now, the state of New York has a very similar definition of a bridge in the highway law, chapter 25-9-230, which reads similarly, structure including supports over depression, over water, railway, traffic track or passageway for carrying bridge, carrying traffic, moving loads, and the center more than 20 feet under croppings of abutments or spring lines or arches. And the term bridge in this section also includes approaches. A little bit different, but very similar. However, there's a caveat to the New York State definition. In a Rockland County case, the Village of Chestnut Ridge appealed a decision, and the appeals court found that a structure, regardless of the span of 20 feet, adopted a functional approach, citing dictionary definitions of bridge and culvert, concluding that this particular structure was a bridge, though it was less than 20 feet. So the village was compelled to, replace it because it was a bridge. So that is the fancy legal way of the New York State Court of Appeals saying, if it walks like a duck, talks like a duck, it's a duck. So we're going to play some yes or no over the next few slides. Is this a bridge? Okay, survey says yes. I said so in the earlier slide, so that's kind of obvious. And it has it's more than 20 feet. It has a roadway. So next one, is this a bridge? Okay, survey says 49 say yes, 49% say yes, 51% say no. So depending on the dimensions, the answer is maybe. If the distance from here to here, from the outside spring lines of the far pipes are more than 20 feet, and the distance between the pipes is less than half the diameter of any pipes, it would be a bridge. If each individual one is less than 20 feet, but they were stretched out apart from one another more than the diameter, it would not be. So you'd have to carefully look at what configuration you have. Okay. So is this a bridge? So we have 76% say yes, 24% say no. And this is another one that falls under the maybe category. If the distance from abutment to abutment is more than 20 feet, yes, definitely it is. If it's less than 20 feet, by the New York State Court of Appeals definition, it's a bridge. But as far as federal National Bridge Inventory System and whether it's getting inspected on a regular basis, the answer would be no, it would not. So again, you have to know the size of the structure. So why does it matter if something is a bridge or not? Well, if it's defined as a bridge, under the federal definition, it falls under the National Bridge Inventory. And if it's on the National Bridge Inventory, it has a unique bridge identification number as shown here on the abutment. This one is 3306230. All bridges, according to federal law and in New York, are inspected every 2 years, every 24 months. The inspection reports are forwarded to the owner for review. I used to have inspection reports coming across my desk throughout the course of the year. So we at the county could see what the conditions of the bridges in our inventory were. And those inspection reports had a lot of useful information, and it gave us a good idea of bridges that we needed to take a closer look at or perhaps schedule maintenance for. The inspections, if the inspectors find issues with the bridge, they may issue flags. In New York, we have a flag system where red flags, yellow flags, and safety flags are issued. Typically, safety and red flags require some sort of prompt action, either 30 days or 24 hours, depending on the severity of the issue. And that action may include closing the bridge. Yellow flags indicate that there's a problem that needs to be closely watched. And typically, if a bridge is receiving flags, it is scheduled for annual inspections or interim inspections to follow up to make sure the situation is not deteriorating anymore. Okay. So bridges versus culverts. So bridges, by federal definition, state definition, have a span in excess of 20 feet. Now, going to the Court of Appeals definition, a bridge has some sort of superstructure supported by substructure elements, and the superstructure, the girders in this case in the photo, carry the loads. And hydraulically, bridges are typically designed to pass whatever the design storm is and have a minimum amount of freeboard. Ideally, you don't want water washing over top of the bridge or into the superstructure unit. Now, culverts, on the other hand, the New York State and federal definition is a span of less than 20 feet. And in practice, we view large culverts for inspections and the like as in the 5 to 20 foot span. But structurally, a culvert is a structure that is buried with the soil carrying a lot of the structural load, and the soil around the culvert transmits the load down into the foundation soils below. And hydraulically, culverts may be designed to be submerged. In this particular case, you probably wouldn't want it to be submerged too much or to overtop. But as you can see with the stone fill on this culvert, it assumes that the water could rise above the top or crown of the culvert during a large storm event. So now we'll talk a little bit about bridge components. The 4 components of bridges include our deck, our superstructure, our substructure, and our foundation. And we'll talk a little bit about each of these in more detail. This is a photo of the Route 2 bridge over the Hudson between Troy and Waterville. And it's got a concrete deck and rail system. It's got continuous steel multi-girder superstructure. The substructure is concrete piers, and the foundation is down below the substructure and is hidden. So what is our bridge deck? Well, it's the part that carries the traffic loads. It's often concrete, and depending on the function of the bridge and who it's serving, it will be designed to accommodate the users. In this particular case, it's a concrete deck. It's got 3-rail vehicular guardrail. If it were to have a lot of pedestrian traffic, a bridge like this, it might have elevated sidewalks and curbs. It might have a higher pedestrian type rail. In the photo we saw earlier of the bridge in Ogdensburg, that has an open grate steel deck, which is lightweight, but that bridge is also not designed or meant to accommodate pedestrians. The deck is supposed to provide a nice smooth surface for traffic to ride over, and a concrete deck or other types of deck also provide a roof or cover to keep moisture and debris from getting down onto the superstructure and substructure elements. The Ogdensburg bridge had the open deck, and as a result, there was some deterioration of the substructure units because of the moisture and going through the deck and corroding. I have a question. What's the guide rail versus pedestrian guide rail heights? The pedestrian rail will typically be in excess of 42 inches because that's the OSHA safe fall protection requirement height, where the vehicular rail will be in the like 34 to 36 inch range. I don't recall the figure exactly, but it's in the New York State DOT standard details for rail. Okay, we move on to superstructure. So this is what carries the load or spans the from abutment to abutment or substructure unit to substructure unit, and it transmits the load from the deck to the substructure. Now, in the photo here, this is a cable stayed bridge. I believe this is the Tappan Zee Bridge down in across the Hudson, and the superstructure elements on this one are the towers, the cables, and the deck elements and girders that the cables are tied into. It may be just a concrete slab. State of Wisconsin has lots of concrete slab bridges. They just form and pour a reinforced slab to span their relatively short spans. The most common thing we see around the country is multi-girders as superstructure units. You'll see multiple steel girders or multiple concrete girders, and those are transmitting the load from abutment to abutment or pier to abutment, between the substructure units. Some of the older bridges for longer spans are trusses. The old Tappan Zee Bridge was a truss. they seem to be a fairly common design and construction method back in the early part of the 20th century to get longer spans. So you will routinely see trusses. They have their own sets of challenges. And then in this particular photo, you have cables, both suspension bridges and cable stayed bridges. Okay. Substructures. Okay. So substructure components, they transmit the load from the superstructure down to the foundation. These are substructure piers on the Tappan Zee Bridge, and on the approach spans, our superstructure is steel multi-girders, steel plate girders, and the substructure units transmit the load or carry from the superstructure down to the foundation. Substructure elements are commonly concrete, sometimes steel. We have the abutments, which are at the beginning of the structure, at each beginning and end of the structure, and then the piers, which are shown here, if intermediate support is needed. And then down below are substructures. We have our foundations, and they may be a variety of things. They transmit the load to either sound-bearing soils or to rock. In this photo here, this is driven H-piles, and they were driven down to rock. Sometimes H-piles may be driven to rely on skin friction. In Texas and other parts of the country, drilled shafts are often used rather than H-piles, just due to the geology. And the drilled shafts may rely on skin friction. Sometimes they will be end bearing. And then commonly in parts of the country where rock is very close to the surface, we may have spread footings. Also, we may have spread footings where we're not worried about scour. You're not over a waterway, and the soils underneath are relatively sound, and we're not concerned about settlement. So we're going to talk a little bit about bridge terms, basic nomenclature. So here, intermediate support is a pier. And then as part of the pier, we have a column. Between columns on our pier, we have or may have a pier cap. Under the columns, we may have a footing or pile cap, and we may have piles if it's supported by a deep foundation. In this particular bridge, we have a multi-girder bridge, so we have girders. We have our deck. We have our span, which is from center line of bearing to center line of bearing of our superstructure elements. And we have our abutment, which supports either the begin or end of our bridge. Here's a composite bridge, a variety of foundations and supports in a longitudinal section. So we have beam seats. We have our pier caps. We have our abutment at the begin end of the bridge. We have columns with a 2-column pier. We have piles and a pile bent pier. And this doesn't have any separate footing or cap. You just have a pile cap, and you just have drilled shafts or driven piles as foundation. We have our beams and girders up here. We have our beam seats where they sit. We have piles supporting our abutment. We have our deck. We have an approach slab, which some bridges may or may not have, but that basically spans from the beginning of the bridge back into the approach embankment and helps to compensate for any potential settlement you may get. We have our roadway. Some bridges at the abutment end may have a berm, which is an area at the top of the slope protection for access to the seats and abutments for maintenance and inspection purposes. We may have a barrier wall, and our span again is from center line of bearing to center line of bearing. And here is a plate girder, and the various parts or components of a plate girder, which include our top flange, which is the horizontal top piece on the top of the girder, bottom flange, horizontal piece on the bottom of the girder, the web, which is the vertical between the top and bottom flange, the connection stiffener, and this stiffener is connecting the diaphragm, K-brace. Terminology varies from part of the country to part of the country, but that connects the girders to one another. Cross frame's another term that's used. And then if the structure is built in composite, designed to be in composite with the deck acting as a stiffening and augmented compression flange, there will be shear studs. And most current bridge construction now, bridges are built in composite, and the shear studs are on that top flange to anchor the deck into the superstructure. So on trusses, terminology for those is the top chord. That would be that top element across the top of the truss. The bottom chord, the element along the bottom of the truss. Diagonals connect the top and bottom chord. Verticals also connect top and bottom chord. And gusset plates are these plates here at the connection points that connect top, bottom, or top, diagonals, and verticals together. And those gusset plates are critical in the performance of the truss. And unfortunately, with the way gusset plates are located and where they often are subject to corrosion and can accumulate debris. Now, underneath our trusses, rather than the multi-girder and cross frame, which we saw in the plate girder diaphragm, we have a slightly different arrangement here where the floor beams span between the two trusses, the truss on either side of the bridge, and then the sleepers or stringers are between the floor beams, and they support the deck. And then we also, with trusses, may have diagonal bracing underneath. Other truss terms, the end of the truss, this is a through truss, would be called the portal. And this would be portal bracing across the top. And then up above, we have diagonal bracing and sway bracing that basically keeps the two trusses acting in unison. So structural performance. How does this all work? Well, the structural elements of the bridge being the deck, the substructure or superstructure resist one or more of the following forces: axial tension, axial compression, shear, flexure, or torsion. And we'll kind of go through where we are. So axial tension, basically, it's a force that pulls along the longitudinal axis of a member, tending to pull it apart. We think back to the photo of the cable stayed bridge. Those cables are in axial tension. And I'm sure it's unlikely they're in compression, because I'm sure many of you have heard the saying, it's like trying to push with a rope. You can't do it. So axial tension members tend to be fairly slender, and they have something pulling on them. Axial compression, it's a force that acts along the longitudinal axis of a member and tends to push the ends of the member together. Examples of axial compression would be a column, because the weight from above is tending to push down and push the ends of the column together. Shear. Now, shear is a force which results from equal but opposite transverse forces, which tend to slide one section of a member past an adjacent section. And when you have shear, you've got vertical shear forces and horizontal shear forces. So as you can see, you've got, kind of equal and opposite. And when something fails in shear, it tends to fail on a diagonal. And places where you have shear forces would be in superstructure elements near the bearing, where you've got the weight of the bridge, all the dead and live loads pushing down, and you've got the reaction at the bearing pushing up. So that's where we tend to have a lot of shear forces, is right near the bearings. Flexure. And what flexure is bending forces, which is caused by a moment, and the moment is typically developed by transverse loading. This would be your beams or girders, where the loading is not along the length of the element, but to the side of it, and tends to make it bow or flex. And what flexure does is it produces both compression and tension in the member. As you can see with this sort of smiley face deformed portion of the girder, is the top is going to be in compression, and on your plate girders and any other kind of girder with a simple span, your top flange is typically in compression, and your bottom flange, conversely, will typically be in tension. So, and because the top flange is in compression, why we often use composite concrete decks, and concrete is very good in compression and resisting compression. So that way we're taking advantage of that material to do a job that it does well. Torsion. This is a kind of force that results from externally applied moments that tend to twist or rotate a member along its longitudinal axis. And it's not something we often think of, but it's something that we do have from time to time, is torsion. Not uncommon to have torsion in curved girders, curved girder bridges. You end up with torsion. In this is the Sunshine Skyway Bridge in between St. Petersburg and Bradenton, Florida. And it's a single line of cables, cable stayed bridge, unlike the Tappan Zee, which had 2 rows of cables from the tower. This particular design, the bridge superstructure elements and deck are subject to torsion, and the shape chosen to resist that in this particular case is a trapezoidal concrete box, and a trapezoidal box is very good at resisting torsion. So that is an example of material chosen and shape designed to resist that torsion force. So shape of members. As I mentioned earlier, tension members may be slender. Seeing the elements of this truss, these eye bars are slender. They're not going to perform well in compression. They're likely to buckle, but in tension, they're doing the job. Conversely, compression members, these built up members with the lacing with a larger, created for a larger footprint, are going to perform relatively well in compression. Shear zone. Very often in shear zones, like around your bearings, if with concrete, you may have additional reinforcing stirrups. With steel bridges, you may have either stiffeners or additional web thickness. High moment areas, which tend to be mid-span. On some of our old built up riveted plate girders, we may have additional thicknesses of steel known as cover plates. And torsion members, as I described before, they may have either additional bracing, as we do with curved girders, with lots of cross bracing and some diagonal bracing, or we may, on a curved or subject to torsion load, go to a trapezoidal box. So, structural performance of girders. This is a multi-girder continuous 3-span, and the way this one performs is you will have a moment here, positive moment. So at mid-span out here, it will have tension in the bottom flange, compression in the top flange. However, right around here, we're going to get a stress reversal, and over top of the piers, we will have tension in the top flange and compression in the bottom flange, because this is acting as a cantilever. So just want to keep that in mind as you're looking at and doing maintenance work on your bridges. Areas with high shear are right around the abutments, and we have the augmented, we have a stiffener here to support the girder and augment the web, because there's a lot of shear here. And were we to have a shear failure, it would likely be a crack or distress that would be diagonal in this direction. You're more likely to see that with concrete. With steel, it's not uncommon to see some sort of deformation if you have loss of strength or failure. So trusses, how do those perform? Well, with a simple span truss, we have compression members and tension members, and commonly the bottom cord is in tension, the top cord is in compression, and the diagonals and verticals may be in tension or compression, depending on how the truss is designed, and it may require some analysis. But if we think back to the photo of the other truss, you can often look at the elements and have a pretty good idea based on how they're constructed, which is a tension or compression element. The tension elements tending to be more slender, and the compression elements tending to have a larger footprint or radius of gyration. For cable bridges, all of the cable is in tension and the towers are in compression, and the deck or deck elements may be in compression, tension, or shear or flexure. So bridge materials, what does what well? Steel is very good in tension. Concrete is very good in compression. Timber is pretty good at both. Masonry is good in compression, but not great in tension. So what we do is use our materials in a way that we take advantage of the strengths of each. So bridge materials, steel, you can do a lot of stuff with steel. You can shape it. It's pretty versatile. You know, here we've got this grasshopper or frame design bridge with steel substructure. Comes in a variety of grades from the old A30s and A36s of the mid 20th century up to, you know, the 70 KSI steel we're using now. As a bridge owner, I like steel a lot because we could fix it, you know, with some plates, bolts, angles. We could bolt things on and repair it. It's good. Steel is great in both compression and tension, but the challenge with steel is it does corrode. So rust is an issue. So good and bad with steel, you can build, you know, elegant, beautiful structures, but the downside is if you don't maintain your steel structures, they will corrode. Concrete, economical, variety of shapes. It tends not to be too susceptible to water damage and is really good in compression. Unfortunately, it's not so good in tension, which requires some sort of reinforcing, and typically we use steel for that. And that tends to be one of the Achilles heels, because if the water gets into the concrete and causes the steel to corrode, that can deteriorate the concrete. So good thing about concrete, you can precast it, you can cast it in place, and it can perform well for years. The bad thing is if you've got water infiltration causing your steel reinforcing to fail, you can start to get cracks, spalls, delaminations, etc., which will require attention. Timber can be early part of the country. It was used commonly in New England where there was lots of it. It resists de-icing agents. It's pretty easy to build. and it is renewable, but it's susceptible to decay, which is why we build covered bridges, because the roof keeps the structural members from the getting exposed to the elements and decaying. The covered part is a protective covering. It is, if you will, the same as painting your steel. So in a dry environment, like the photo on the left in South Dakota, timber is great. In a wet environment where it's unprotected, as seen on the right, it tends to decay and deteriorate. So things to look for. The bridge maintenance credo includes the self-evident truths that all concrete cracks, all joints leak, and rust never sleeps. So keep that in mind when you're looking at your bridges. In steel, you want to look for corrosion and section loss. You want to look for where it's been hit or there's impact damage. If you have corrosion and section loss, like we do under a leaking joint in this photo, you'll want to look for any distortion or buckling, broken connections. In this case, we have failed protective coatings, and if you have debris accumulating, it can accelerate the failure of your protective coatings and then lead to corrosion and section loss. For concrete, you want to look for cracking. You want to look for efflorescence, which is leaking water and minerals leaching out through it. Soft or unsound concrete. Is your rebar exposed? If you have pre-stressed, do you have tensioning strands that are exposed? And are they damaged if they are? For timber, do you have splits and cracks? Do you have any crushing? Is it moving at all? Do you have decay and insect damage? Any moisture damage? Here in this photo, we've got lots of moisture damage leading to decay. And if you have accumulated debris, that can accelerate the moisture damage and decay. On your substructures, things you want to look for. Is your back wall rotating or tipping? How does that construction joint look between the back wall and the abutment? Between the beam and the back wall, do you still have clearances? Your wing wall, is it plumb? Do you have evidence of movement? Any cracking under the bearing? And are your weep holes functioning? Substructures on your piers, are they still plumb? Do you have any deterioration up around the pier cap? How do the columns look? If you have deterioration in your column or substructure units, it's often right near the ground or mud line or water line, so you'll want to look there. Joints, they can be the Achilles heel of bridges. Do you have any staining or ponding water on the abutment, pier cap, or back wall? Is there obvious leakage? You know, in this case, in the photo, we can see rusting beams because the joints have been leaking. And if you're down under the joint, can you look up and see daylight? Bearings. You have a lot of debris. Are your anchor bolts loose? Is everything aligned where it's supposed to? This particular photo shows an elastomeric bearing that's overextended. We would expect to see something similar to this after a week of 100-degree days, but if it's wintertime and cold, this would be a red flag that something's going on with our bridge. Do we have corrosion at our joints? And are our bearings moving like they're supposed to? And if they're sliding plates or other types of older bearings, are they lubricated? So now we're going to roll into our poll questions. So by the federal definition, a bridge is longer than how many feet? 55, 30, 20, or 100? Okay, 92% said 20. That is the correct answer. Okay, next question. What forces tend to twist structural members? Flexure, shear, compression, torsion, or tension? Okay, 94% said torsion. That is correct. Okay. What distress is not something to look for in steel bridge members? Corrosion, distortion, debris, impact damage, or decay? Okay. Okay, in steel bridge members, decay is something you don't have to worry about. That's unique to wood. Corrosion is common. Distortion can happen. We can accumulate debris and we can get impact damage. Okay, so what part of the bridge carries the load from the deck to the substructure? A, superstructure, B, foundation, C, deck, D, joints, or E, bearings? Okay, the answer we were looking for is superstructure, and in some cases, the bearings are considered part of the superstructure. So from the deck to the substructure. So the answer we were looking for is superstructure, and bearings is kind of a trick question. Okay, so anybody have any questions for me? And if not, I want to thank everybody for joining me this morning, and I hope I either didn't bore you to death or put you to sleep. So, okay, I have okay.
Thank you, Willie. And if you guys do have any questions, you can always reach out to us at the New York State LTAP Center. We can get them over to Willie. All right. Enjoy the rest of your Tuesday. Thank you again, Willie, and thank you guys for joining in.
Thanks a lot.
Bye-bye.